In this session, I want to start a new topic that is about DC machines. So, the term electrical machine is a general term used to include electrical motors and generators, as we have discussed so far. So, actually, transformers are also coming into electrical machines category, but here we will talk about motors and generators, and mainly motors. So electrical machines are used to perform electromechanical energy conversion, right? So electrical machines are used to perform electromechanical energy conversion. That means electrical to mechanical energy or mechanical to electrical energy. So when we consider electric motors, uh, it convert electrical energy into mechanical energy. Electrical motors convert electrical energy into mechanical energy. Then electric generators are doing the other way around. They convert mechanical energy into electrical energy. So the electrical generators convert mechanical energy generated maybe from the uh, water or maybe some other gas turbines or whatever it is. The mechanical power produced will be converted into electrical energy. So they are called electric generators. For example, very simple example, if you have seen the dynamo on the normal push bikes, so that is a generator. It is using the power of the wheel tire into the electrical energy, right? So in electrical machines you can see a number plate, name plate like this, which gives lot of information about that particular motor, like the manufacturer's name, the designation of the model and the size, the type of current, type of machine, lot of information on the nameplate. But this is just to show you the nameplate, but later we will discuss further about this one, right? So the electrical machines actually are using two physical principles, uh, both generators and motors. First one is the principle of electromagnetic induction, that is introduced by Faraday in 1831. He basically found that moving a permanent magnet in and out of a coil of wire induce current in the wire, right? So if you move a permanent magnet in and out of a coil, it will generate some uh, current, right? So this principle is used in generators. And the second principle is called the principle of electromagnetic reaction. It was introduced by Ampere in 1820, which says a conductor carrying a current placed in a magnetic field results in a displacement, that is the conductor experience a force, and this principle is used in electrical motors, right? So I hope you remember these things when we discuss about electromagnetism. um, if there is a relative movement between the magnetic field and a conductor uh, at a certain speed, we found that magnetic field is generated. Sorry, the EMF will be generated on the conductor if you if there is a relative movement between the magnetic field and the conductor, so that the conductor is cutting the magnetic flux lines, then there will be an EMF or current generated on the conductor that is used in generators. And the other one, if you place a current carrying conductor in a magnetic field, then there will be a force on the conductor, right? So that is what we use in the electrical motors. So if we first thing we are going to talk about DC machines, which are DC generators and motors, but the construction wise, both the generators and motors look same, right? So basically a DC machine can either operate as a motor or generator, right? So it can convert both electrical to mechanical power or mechanical to electrical power. The application of DC machines as a motor is very much prevalent. That means very much used than using a DC machine as a generator, because normally nowadays it is much easier and readily available, the commercial AC supply, which we can easily convert into DC by using static devices. So that means there are no mechanical movements required to generate DC at the moment, right? Therefore, motors are widely used than DC generators. As you have already studied under electronics, by using a diode bridge, you can convert AC into DC very easily, and also it is very reliable, low maintenance, right? So when we consider DC motors, there's a wide range of speed and torque accompanied by high overall efficiency. The DC machines, uh, you can get a wide range of speed and torque, which is accompanied by high overall efficiency. So DC motors have a wide range of applications in the day-to-day life. For example, for household appliances like fans, pumps, portable electronic, and automobile applications. Mainly the fans in your homes are mainly AC fans, but sometimes in vehicles, and if you have battery powered fans, they all are using DC motors, and especially portable electronics. What mainly electronic circuits are using DC power, especially when we have to make it portable. Otherwise, you have to give the power through a wire, which will prevent to take it and move, right? Therefore, for portable electronics, we have to use DC motors. And automotive applications, like nowadays the electrical cars are using DC motors. And also the applications where you need very high torques, like conveyor belts, lifts, hoists, punch presses, they are using DC motors due to the wide range of torques and the speeds available with DC motors. Um, if you have seen the punch presses, if you have visited such place, you will see very big iron structures are moved using DC motors to cut metal sheets or bend metal sheets. We are using punch presses. So they are the applications of DC motors. Then, however, the development of adjustable speed drives has demonstrated that the same performance can also be achieved with uh, AC machines, which we called induction machine with a power electronic converter, right? Therefore, nowadays, induction motors or induction machines are very much popular, um, mainly because they are cheaper to manufacture, um, and also very much easier to maintain than DC motors. You will understand why it is easy to maintain AC machines than DC machines when we talk about the real inside construction. So basically, uh, if I show you the varieties of electrical machines in one single slide, this is a good demonstration of that one. You have electrical machines, three types: DC machines, AC machines, and special machines. So DC machines can again be divided into two categories. One is self-excited and the other one is separately excited. We will talk about each type in detail later. And again, the self-excited DC machines will be either series, shunt, or compound. That is the way the coils of the field winding and the armature windings are connected, whether they are series, parallel, or a combination of series and parallel, which is called the compound. And then you might have separately excited. That means the windings, the armature windings and the field windings are separately excited. But I am not going to explain those things because you are still not familiar with the terminology. And then we have AC machines. It is again divided into two types. One is induction, the other one is called synchronous. And then the induction motors are again divided into single phase and three phase. And then we have special kind of machines like switched reluctance machines, brushless DC motors, and also stepper motors, which you use for robotic applications. And then we have something called linear motors, right? So but in today's lecture I'm basically concentrating only about DC machines and its internal construction, and then we will go into uh, more deeper we will go more deeper into DC machines later, and after that we will be doing AC machines as well. So now let's get familiar with the terminology before we understand the way the DC motors are working. So all motors consist of the same basic components. They are called stator, rotor, commutator, and brushers. Right? Stator, rotor, commutator, and brushers. So stator means the steady part, rotor means the rotating part. Commutator is a special kind of device which is used to uh, interchange the directions of the current supply or current uh, generated. Uh, the directions will get automatically changed due to the commutator. And then we use brushes to give power to the rotating components, that is the armature. So they are called brushes. So let's look at more detail on these three, basically these four items. So if you look at the very simple diagram of a DC motor here. Uh, the first item which is rotating in the middle is called the armature or the rotor, right? This middle part is called the armature or the rotor. Then I will come to the next important part. It's called the field winding, third one. I will come back to the interpole later. Field winding. Field windings. Here you have two field windings which generate a magnetic field using electrical energy, which will make this pole as north pole and this pole as south pole. So there will be a strong magnetic field generated across the armature like this from north to south. And then other parts like housing or the frame of the motor is called the yoke. And then you have the terminal box where you connect the internal windings, either armature or the field windings or the interpole windings into the outside power sources, DC sources, right? And if you look at the middle part separately, that is called the armature or the rotor. It consists of a steel shaft, that is this steel shaft here, and a stack of laminations. So the middle part is something like this. These are actually laminations of this shape, which is combined together to form one solid armature. But instead of using laminations, if you use solid iron as the core, then you know the eddy current losses will be very high, and the core will get heated up, and there will be a lot of power loss as well. To prevent that, it has been laminated, right? And then uh, the windings are actually going through these slots here, uh, and then this part, the little smaller, with the little smaller diameter than the windings, is called the commutator, right? This is the commutator, and then this is the steel shaft. And if you look at carefully on the commutator, the cross section is shown here. This is the shaft. Number 8 is the shaft, and then on the shaft we have fixed number 2. The number 2 is the end ring, but this number 3 is the running surface, that is the actual surface, and number 4 is the brush, carbon brush, right? So and then the shaft and this number 5, which is the copper segment, the copper slots, which you can see here, they are actually insulated using mica like thing. Number 7, the dark color one, is the insulation. Though these are metal strips connected onto the shaft, right? So basically the commutator consists of copper bars or segments with mica insulation in between. So this is called the mica insulation. The segments must be insulated from each other and from the support as well. So two segments here, two segments are insulated, and also it is insulated from the shaft as well. So each segment is connected to the armature winding by a solder connection. So that it is basically going into this place number 6. The coil end is connected here, so that when you give the power through the brush, it will go into the coil and it will generate magnetic field. In general, the diameter of the commutator is smaller than the rotor diameter. Right. So the task of the commutator, as I mentioned earlier, it is basically doing AC to DC conversion or DC to AC conversion. Uh, there is always alternating current in DC generators. If you use a DC machine as a generator, it will normally generate uh, AC current, but they have to generate DC current. So this AC current is changed into pulsating direct current by the commutator. So when we say AC, let me draw it and show you. When we say AC, it is something going like this, no? But when in DC generators, through the commutator, when this power is coming out, it is coming like full wave rectified waveform. I hope you remember these things. Something like this, it is called the pulsating DC, right? And that is on generators. The same process occurs in reverse in the DC motor. For a DC motor to work, it needs AC, alternating current, but we are feeding DC, so the commutator will convert DC signal into AC signal, which we will understand when we discuss about the operation of a DC motor, right? Then we come to the stator. So stator is the steady part, a stationary part of the DC motor. It's called the stator, right? So it consists of rolled steel ring. This is a rolled steel ring with 2 or more field poles. So these field poles, here in this case 4 poles, are connected into the stator frame. The field poles are metal pieces made of thin sheets of steel laminated together and mounted to the field frame for the field winding. So if you enlarge one of these poles, you will see it is again laminated one, and the coils are wound around these poles. They are called field poles, right? Then if you look at other poles that we have here, these are the 2 main poles, and in addition to that we have smaller poles which are called interpoles or auxiliary poles placed between the main field poles. And again these poles are carrying some coils, and these coils are seriously connected with armature windings, right? So one of the end of this coil is connected to the brushes to give the current to the armature windings, and then coming out here and going back to the power supply. So one end of this interpole winding is connected to the brush, and the other end is connected to the DC power supply. So to explain the interpole function, I have to take a lot of time, so I'm not going to explain it here. But remember, in a simple manner. Uh, these interpoles are made with large size wires. The thickness of the wire is normally larger than the armature windings. Um, and also the pole size is smaller than the field poles. The wire thickness is larger because they will carry a larger current than the armature windings. Um, so these interpoles are sometimes known as commutating field poles. Commutating field poles. The role of the interpole is to compensate for the neutral plane shifting caused by the armature reaction when the load current changes. We will explain that when we are familiar with the operation of the DC motor. And then that is about the stator. Then if you closely look at the rotor, or sometimes it is called the armature. So this is the part which actually rotates inside the motor, and it provides the mechanical energy at the end of the shaft. The armature is again similar to the field poles. They are again produced with laminated steel sheets. It's a stack of laminated steel discs made of magnetic steel alloy pressed onto a steel shaft and provides slot to accommodate and support the coil of wires. So this is one piece of the one lamination on the rotor. So here these are the slots for the windings, and then you can have wedges so that you can hold the coil inside the slot. And also in the middle you have some holes made like this just for the ventilation and cooling of the rotor. Then we come to the next one, the laminated steel core prevent the circulation of eddy currents. Again here the core is laminated to prevent eddy currents. Sometimes eddy current is called the Foucault current as well. If as I explained earlier, if the core were solid, then the magnetic currents or eddy currents will produce and circulate in the core material near the surface, and which will cause core material to heat up. So to prevent that, the rotor is made from laminated sheets. Laminated core also prevents other magnetic losses called flux losses. And then by preventing these losses, you can strengthen the magnetic field. Then the flux losses and eddy current losses are grouped together by designer and called the core losses, as we discuss under transformers. Then we come to the other important part, which is called the commutator. So the commutator is actually constructed using number of copper segments insulated from each other by mica and mounted on the motor shaft. As I showed you the construction of the the commutator, these copper segments are insulated each other, and it is also insulated from the shaft. And then the armature windings are connected to the commutator segments. All the coils, they are called armature windings. These windings are connected to these copper segments, commutator segments. The commutator acts as a current reversing switch. It automatically can reverse the current or change the direction of the current when the rotor is rotating. So it will make sure that the current is always flowing in the same direction around the coil, right? So relative to the fixed magnetic field. So it otherwise, you know what will happen when the coil is rotating, the direction of the current remains same of a particular bar, then the force will be directly opposite. Therefore you can't rotate. So if you need to rotate, then we have to uh, the armature windings are connected to the commutator segments. The commutator acts as a current reversing switch, automatically reverse the current um, to ensure that the current is always flowing in the same direction around the coil relative to the magnetic field. So otherwise the motor will start to vibrate backward and forward. To prevent that and allow the rotor to continuously rotate, um, we have to reverse the current uh, uh, when the coil is turning. For that we use the commutator. And then the other important part is the brush that will give the power to the commutator, and then in turn it gives the power to the armature windings. So they are called brushes. The brushes provide the physical connection of the external power source to the armature. The brushes provide the physical connection of the external power source to the armature. So these brushes are made out of carbon or graphite, uh, and typically they are spring loaded to make sure the permanent contact, continuous contact with the commutator. You know, when the commutator is moving, when it is, and also moving, touching the segments, commutator segments, what will happen after some time of operation? The brushes will wear out, and then it will affect the connectivity. To prevent that, these brushes are spring loaded, so when it is wearing out, it is pressed into the commutator, so that there is a very good permanent connection between the brush and the commutator, right? So this is basically the parts of a DC motor. If I combine all them and show you, you will see a diagram like this, where you have the housing or the stator here, and the middle part, which is called the armature or the rotor, and then you have the commutator here, and the brushes are not shown here, but brushes will be touching the commutator. And then in addition to that, for mechanical movements, you have to have bearings at both sides, which supports the shaft, so that it can rotate inside the stator. And sometimes there might be a fan like this connected to the shaft, which will uh, allow air circulation through the inside of the motor, so that it gets automatically cooled. Right, then if you look at the armature windings with some photographs. The armature windings are like this. Uh, Sometimes these windings can be um, done through manual by hand, or you can use some automated field winding winders, automatic winders to wind up these coils. And then how these coils are going through the slots of the armature and getting the power. If you look at, uh, you will see that uh, uh, the rotor drum surface is having these coils, uh, and the two associated conductors which is forming the coil um, are electrically displaced by approximately 180 degrees. So as we already know, the main task of the commutator uh, is to produce DC current from the generated AC in the case of a DC generator. Um, so it will basically convert the AC signal generated by the armature and outputting a pulsating DC. It's like full wave rectified signal of an AC waveform. Um and in the case of motors, the same process will happen in the other way around, in the reverse direction. Uh, because for a motor to rotate, we actually need alternating current, but we have to provide DC for DC motors. Then this DC is converted into alternating current using the commutator. Right, I hope you got some basic understanding on the construction of the DC motor, and you know the parts of it, like stator, and then which is the stationary casing, and then the rotor, which is the rotating part. Sometimes we call it the armature. uh, Let me show you it again uh, by using this. So this is the armature, which is the rotating part, and then we have the stator, which is the stationary part, and on the stator we have field poles. These are called the field poles, which generate the magnetic field required for the DC motor. And armature is having coils which is powered by the brushes, and these brushes getting the connection through the interpole windings from the DC power source. Uh, then we talk about stator construction and the function, and then the rotor construction and the function, and then the commutator, how it is constructed and what is the function of it, and then finally the brushes. Uh, so I hope you understood that, and I will try to show you some video clips related to DC motors, so that you can understand in a better way how the construction of a DC machine is and how they are getting operated in my next lecture. Thank you very much.